Imagine you have to animate 1,000 individual moving parts. Doing that by hand, frame by frame, is a logistical nightmare. That traditional method of dropping keyframes onto a timeline is entirely unscalable. If a client asks for a timing change, you have to hunt down and manually adjust every single point. We can bypass the timeline entirely by using autonomous VFX mechanics. We write simple mathematical rules that tell the software exactly how to behave. Today, we are going to build a fully automated proximity effector system. Our shapes will react dynamically to a target object, and we will do it without setting a single manual keyframe. Mastering logic allows you to optimize your workflow, ensuring that even complex scenes remain responsive and render efficiently on your current system. To automate movement, we first need a pulse. In After Effects, the math.sin expression generates a smooth oscillating wave. It gives us a reliable way to make an object breathe or hover. When we bind that sine function to the composition's time variable, the software calculates the movement completely continuously. As the clock ticks forward, the wave goes up and down forever. This diagram shows how the sine wave maps directly to our object's physical scale. If we multiply that wave by 10, we increase the amplitude. The peaks get higher, the valleys get lower, and the object scales larger. Doing this manually requires plotting high and low scale points across your entire timeline, copying, pasting, and hoping you never need to adjust the frequency. By writing a single line of code, the animation takes care of itself. You establish the rule, and the software handles the execution. Step 2 is making our shape react to its environment. We will set our layers to calculate their own scale based on their physical distance from a designated target null object. To achieve that, we use the length function. This operates as an invisible tape measure, constantly calculating the exact pixel distance between our shape and the target. Here on the left, we have our target node and our object node. On the right, we use the linear function to connect them. It maps that raw distance directly to a scale percentage. The closer the target gets, the higher the scale value rises. Mathematics will give you exactly what you ask for. If the target moves extremely close or incredibly far, the equation pushes past our intended boundaries. This forces the scale into negative numbers or absurd sizes. We fix this by wrapping our equation in the clamp function. This builds an absolute safety fence. It intercepts the raw math and snaps those values securely between our chosen minimum and maximum limits. By using linear to bridge the data and clamp to enforce the rules, your static objects transform into a stable, spatially aware system. Next, we need organic variation so our objects don't behave identically. It is tempting to use a basic wiggle expression, but that recalculates a new random path every single time you press play. You can't review or render it consistently. The professional standard is probabilistic VFX methodology. This exact technique relies on generating perfectly controlled, mathematically reproducible randomness. This grid shows how the math plays out. By adding the command seed_random index true before our wiggle, we tell the software to use the layer's numerical position in the timeline to determine its fate. It generates and locks its unique flight path permanently. Because of that rule, you can take a single layer and duplicate it 20 times. You generate a swarm of objects all reacting independently, based strictly on their layer number. You achieve the complex visual variation of an organic system, but with the strict reliability required to safely hit render. Building smart systems creates a new challenge. If you link layer after layer recursively or stack dense calculations, the software has to recalculate every step on every frame. This will heavily tax your CPU. This is the composition profiler, toggled using the snail icon at the bottom of the timeline. It displays the exact render time for every element. That red warning indicator shows us exactly which expression is causing the bottleneck. Once you locate the bottleneck, you perform optimization triage. Select the heavy layer and use the keyframe assistant to convert that complex expression into raw keyframes. The software solves the math once, and the heavy lifting is done. Optimization is diagnosing the data and neutralizing your bottlenecks. Here is the final output. As the target orb moves, 20 unique layers use our logic to react, scale, and settle in real time. Checking our profiler, the render times remain completely green. If you save this logic cluster as an animation preset, What used to require hours of manual adjustments becomes a 5-minute setup you can deploy in any future project. As a curator of logic, you design the rules that govern the motion. The software handles the execution.